Welcome back to the deep dive. Today we are taking a shortcut, really, through one of the most beautiful and complex areas of physics, the behavior of fluids.
We're diving into Chapter 40, which is called The Flow of Dry Water.
Dry water. I love that. It sounds like a total contradiction.
It does, but it's our essential starting point. We're modeling an idealized fluid, you see. It's incompressible, so its density never changes, and it's totally frictionless.
Non-viscous.
Exactly, non-viscous. We've basically stripped away all the messiness of the real world, like friction, so we can find the absolute fundamental rules that govern things like, streams and whirlpools.
And that's our mission for this deep dive? To find that structural blueprint for hydrodynamics, the fluid version of Newton's laws.
Right.
And what's just amazing and something for you to keep in the back of your mind here is how the rules we find for this perfect fluid, they have this deep, almost shocking mathematical symmetry with the laws of electrostatics.
It's a beautiful symmetry. It tells you you're looking at pure structure. So we'll move systematically. We'll start with fluids at rest hydrostatics. Then we'll get them moving. And finally, we'll look at the physics behind those spinning structures, like vortices. Okay, let's do it. Section 1, hydrostatics. So if our ideal fluid is perfectly still, what forces are actually acting on it? Well, only one: pressure. Because we've assumed zero viscosity, there are no shear forces.
So nothing is trying to slide layers of fluid past each other.
Nothing at all. The only force is pressure, and it always has to push perpendicular or normal to any surface it touches.
So if I imagine a tiny little cube of this fluid just sitting there, the pressure pushing in from the left has to be exactly balanced by the pressure from the right. It's in equilibrium.
Correct, unless there's an external force.
Like gravity.
Like gravity. Gravity pulls down on that little cube of fluid, so that downward force has to be perfectly balanced by more pressure pushing up from below. This means the pressure has to change with distance.
That's the pressure gradient.
Right. The pressure gradient has to exactly counteract that external force from gravity.
And the big takeaway for you here, for this ideal incompressible fluid under gravity, the pressure relationship is actually really, really simple.
It just increases linearly with depth.
That's it.
If you're in a pool of this stuff, the pressure only depends on how deep you are. You can move sideways, left or right, and the pressure doesn't change at all.
Because you've got the same weight of the fluid column above you.
Exactly.
Yeah.
That's the easy part. Now for the real challenge. Section 2, getting our ideal fluid moving. Now, velocity can vary everywhere, in all three dimensions, and over time. It gets complicated fast. We need a way to describe the flow at every single point. So we start with law number 1, conservation of mass.
Continuity equation.
Right. And since our dry water is incompressible, mass conservation tells us something very specific. The flow has to have zero divergence.
Zero divergence. Okay, what does that mean physically for the flow lines of the water?
It means the flow lines can't just start or stop in the middle of the fluid. There are no sources, no sinks. Every drop of water that flows into a little volume has to be matched by a drop flowing out.
And there's that connection again.
There it is.
Yeah.
That mathematical rule zero divergence is the exact same structural law that tells us magnetic field lines can't start or end anywhere. They have to form closed loops.
Incredible. Okay, so that's law 1. Law 2 is conservation of momentum. Force equals mass times acceleration. And this is where, it gets really tricky for fluids. Why is it so much harder to track acceleration for a water particle than for, say, a billiard ball?
Because a solid object is simple. Its velocity changes over time. But a fluid particle is constantly moving through a velocity field that is itself changing from place to place.
Oh, right. So you have two different things causing the acceleration.
Precisely. First, there's the local change. The velocity at a fixed point in the river might be getting faster. But second, and this is the key bit, the particle itself moves to a new spot where the river is flowing faster anyway.
So you have to track that spatial change, the convective term.
You do.
It's like you're in a boat. Your acceleration isn't just from you hitting the throttle, it's also from steering your boat out of a quiet bit of the river into the main fast-moving current.
That's a perfect analogy. You have to track your speed relative to the water and the speed of the water itself.
So we combine those two effects to get the total acceleration.
And we set mass per unit volume times that total complex acceleration equal to the forces, the pressure forces and gravity. And when you write that all out, ignoring viscosity, you get Euler's equation. That's our master equation for ideal fluid motion. Okay, so now that we have this incredibly complicated Euler equation, let's try to simplify things a bit. Section 3, steady flow. Let's look for a statement about energy.
Right. In steady flow, the velocity pattern itself doesn't change over time. If you look at one spot, the velocity vector there is always the same.
Like watching water flow through a well-designed pipe. It just looks constant.
And in that case, we can trace the paths of the fluid particles. We call those streamlines. And here's the magic. If we take Euler's equation and we analyze it along one of these streamlines, out pops the conservation of energy, which we all know as Bernoulli's theorem.
It's a beautiful result. Bernoulli's theorem says that the total energy, which is the sum of three distinct things, has to stay constant along that streamline.
And those three things are?
First, pressure, or rather pressure divided by density, which is related to work done by pressure. Second is the kinetic energy, 1/2 v squared. And third is the potential energy from gravity.
So there's a trade-off. That constant sum implies a trade-off.
A fundamental trade-off. If you make the fluid go faster, you increase its kinetic energy. So something else has to drop to keep the total constant.
Either the pressure or the height.
Exactly. If the fluid moves upward against gravity, its potential energy goes up, so either its speed or its pressure must go down.
Hold on. Is that constant the same everywhere in the fluid, or just along one little path?
That is a critical question. It's only guaranteed to be constant along one specific streamline. However, if the flow is also free of any swirls, if it's irrotational, then the constant is the same everywhere.
Let's visualize this. The classic example is water jetting out of a small hole near the bottom of a big tank.
Right. If we apply Bernoulli's principle between the still water at the very top of the tank and the water shooting out of the hole, you see a clear energy conversion.
The water at the top has potential energy because of its height, but basically no kinetic energy. And as it falls that height and shoots out the hole, it converts that potential energy into kinetic energy. This gives us Torricelli's result.
The speed of the water coming out is the same as if it had just freely fallen that distance.
Yeah.
And what about a horizontal pipe that gets narrower, a constriction?
Well, the continuity equation demands that the water has to speed up to get through that narrow section.
And if the speed goes up, Bernoulli's theorem forces the pressure to drop dramatically. Speed is gained at the expense of pressure. That's why a shower curtain gets sucked inward when you have the water on full blast. The fast-moving air and water spray creates a low-pressure zone. Love that. Okay, finally, section 4, circulation and vortices. This brings us back to that idea of irrotational flow. What does it mean for a flow to be completely irrotational? It means if you could place a tiny imaginary paddle wheel anywhere in the fluid, it wouldn't spin.
It would just move along without rotating.
Exactly. Mathematically, it means the curl of the velocity field is zero everywhere. We call that curl the vorticity.
And here we are again, back at that deep mathematical symmetry.
It's really something.
Yeah.
If the divergence is zero, that was mass conservation, and the curl is zero, meaning it's irrotational, well, the mathematics describing that flow is identical to the math for an electric field in a region with no charges.
Amazing. So if vorticity is the local spin, what's circulation?
Circulation is related. It tells you about the overall rotational nature of a flow path. You take a closed loop in the fluid, and you integrate the velocity all the way around it. For completely irrotational flow, that circulation is always zero.
But whirlpools exist. I've seen water draining from a tub. It spins like crazy near the center.
It does. That's because if you draw a loop that encloses the center of that whirlpool, it does have circulation. The flow itself is irrotational everywhere except for that central axis.
So the axis is like a singularity.
Precisely. It's like a wire carrying a current. The magnetic field it creates has circulation around the wire, even though the field is curl-free everywhere else.
So what's the big physical consequence of all this for our perfect frictionless fluid?
It's Helmholtz's theorem. It's a massive statement. It says that for ideal flow, circulation is conserved. The vortex lines, the center lines of all that spin, are basically frozen into the fluid. They get carried along with it.
They can't just appear or disappear.
They can't start or end in the middle of the fluid. They have to form closed loops or stretch all the way to a boundary.
So the reason a smoke ring can hold its shape and travel across a room is, it's a direct consequence of this conservation rule for a perfect fluid.
Absolutely. It's conservation of angular momentum in action. If you could somehow grab that smoke ring and stretch it out, making its radius smaller, the spin velocity inside would have to increase like crazy to keep the total circulation constant. It's an incredibly stable structure.
Wow. So let's recap. We started with the simple forces in hydrostatics, then we built the two big conservation laws for moving fluids, continuity for mass, and Euler's equation for momentum.
From that, we derived the energy principle, Bernoulli's theorem, and finally we saw how these strict conservation rules govern spinning flows and vortices.
I think the main takeaway has to be that the mathematical structure is what matters. By stripping away friction, we revealed that the fundamental rules of hydrodynamics are mirror images of the rules for electrostatics and magnetostatics.
This shows these conservation principles are just universal.
They are. So here's a final thought for you to chew on. This perfect, frictionless model we've been discussing, it mandates the absolute conservation of circulation. It says vortex rings should be eternal and perfectly stable. So what fundamental insight does this strict, perfect mathematical world give us about why real fluids, which are messy, full of friction and viscous, still manage to create such persistent, beautiful structures like smoke rings and whirlpools? The perfection of the model somehow seems to define the behavior of the imperfect real world.
That is something to think about. Thank you for sharing your sources and diving deep with us today.
Until next time, keep exploring.